Okay. All right. So let me screen share. Okay. Which one do you guys want? Do you guys have questions that you guys want to go through first?
I have one question.
Okay.
I am on chapter 8. I have a question.
Yes. Okay. Chapter 8. Which one?
26.
Improper and misc or
Yes.
L'Hopital. Okay.
Improper and misc.
L'Hopital. Okay. I'll use Microsoft Whiteboard if it opens, just because I like the layout of the software. But if not, then I'll just use Annotate Teacher. Okay. 26. This one?
Yes.
Oh, okay. Fun, because I think I struggled on this one a little bit too. As far as I can remember. Let's see. Okay, this is still loading. So what I'm gonna do is probably just open up Paint for now. That'll probably be easier to work on because there's not enough space here. So what I don't like about this problem is what I don't like about these problems in general, but you have to do just because that's how math works, is you have to write limit as b approaches infinity or limit as a approaches infinity like 50 times. You understand what I mean? Because it's an improper integral, you're gonna have to deal with that. But it's nothing we can't do. We can definitely do it. Okay, let me use a different color. Let's use orange. I like the color orange. And perhaps a little bit thicker. Maybe let's use the paintbrush.
MG?
Yeah.
Quick question. So this the final exam is over 5, 6, 7, and 8, right?
To my knowledge, yes.
Okay. All right.
Okay. All right. So, Shruti, since you asked, and if you're not comfortable, you don't have to do it. But how about you go through what you can, and then I'll help you wherever you get stuck. Would you do that, or would you rather just I go through the whole thing? I'm fine either way. I just think it'll help you more. Huh?
Okay, I can try.
Yeah, that's fine.
Okay.
Yeah, that's completely fine. Whatever you can do. So f of x equals negative ln x, and it's important to recognize the range. We're only going from 0 to x is less than or equal to 1. Domain. Why is this domain important? Why do you think? What does the graph of ln x look like? Looks like this, right? So thus, negative ln x would look like this. The reason why we stop at 1 is because if we don't, then we would have to break up our integral from here to here, and then from here to here, because the area is, at one area, the area is negative. We know area is always positive, but in this section, the area would be negative, whereas this section, the area is positive. So they're trying to make it a little bit easier for us by just looking at the integral from 0 to x to 1. Okay. Now determine whether region R has finite area. How can we figure out whether region R has finite area? How do we calculate area?
Would be the integral of from 0 to 1.
0 to 1 of
negative ln of x.
Negative ln x dx, of course, right? Now there's a problem with this. What's the problem? And anyone can chime in.
Ln of 0 is non-existent.
It doesn't exist, exactly. So how do we fix that problem?
So you would create a limit.
Exactly, limit as
a variable approaches 0.
So I usually, just for standard, just for my own sake, what I do is whenever we're dealing with the bottom one, I say a approaches 0, and then whenever it's the top one, I say b approaches 0. It doesn't matter, but it just makes it easier for me to remember. Okay, limit as a approaches 0 of integral from
a to 1
of negative ln x, right?
Yes.
Now this negative is going to cause me just anxiety, so what I'm going to do is I'm going to bring this negative out front, right? But it shouldn't matter. But I'm going to put this negative sign in the very front. Okay, negative limit as a approaches 0 of the integral from a to 1 of ln x dx, right? Now we have to use, how do we figure out the integral of ln x? Do you remember? Let's think about it. Do we know the integral of ln x right off the bat? We can't use an integration table. Can we use a u sub here? No. Can we use is this a rational function? No, so we can't do partial fractions. So what's our only method left that we are comfortable with? Integration by parts, right? Integration by parts. And now you might be thinking, how do we do integration by parts on this? So what we're gonna do is I think most of you guys are comfortable with I use the DI method, which is a tabular method, but I don't think most people are comfortable with that. Would you rather do it with the U and the DV? Is that more comfortable? Okay, all right, we'll do that. So you have a U, and then you have your DV, and then you'll have a DU, and you'll have your V. Did I set this up properly? I'm not comfortable with this method. It should be correct. Okay, because that's what we do in the tabular method too. But U, dv is the function you're going to have to integrate to get to v, and u is the function you're going to have to differentiate. So can we differentiate, can we integrate ln of x? That's what we were trying to integrate. So it wouldn't make sense making that dv. We have to make this one u, ln x, and then dv has to be 1, or I guess you could say dx. You could say this is a dx. That makes sense too. So if this is ln x and then this is dx, once you integrate this, what are you going to get? The integral of dx is just x. And then if you differentiate this, you're going to get 1 over x dx, right? Right? Does that look right? Okay. So then, of course, we know that this is going to equal uv times, this is going to equal uv, minus the integral of v du. So uv will just be ln x. And now we're going to do this in our head a little bit, because you're going to have to learn to do this in your head on the AP exam. So let's just practice that. The integral of v du. So if I multiply x over x, what do I get? 1. The integral of 1 dx is just x. So it'll be x, it should be x ln x is equal to x ln x minus x. Do you see where we got that from?
Yes.
Okay, good. So this will be the negative limit as a approaches 0 of x ln x minus x evaluated at a and at 1. Now let's go ahead and do the evaluation. So we still have our negative, I'll just write L for limit because it'll take too long. Negative L limit of a approaches 0 of, now let's substitute these in. What is ln of 1? Ln of 1 is 0, so this first part will be 0, minus 1, so minus 1 is here, and then a minus sign, and then in parentheses, we do a ln a minus a, right? Now we're trying to calculate the limit of this, right? Now, a approaches 0, right? So if we know a approaches 0, we can say that this portion, the minus a part, will approach 0, so we can forget about that. So what's really going on is this is equal to negative limit as a approaches 0. And actually, what I'm going to do at this step is I'm going to bring the negative 1 out front, because it's not affecting our limit, right? I can bring the negative 1 out front. If I bring the negative 1 out front, I have to multiply by the negative sign. So it becomes 1, right? 1 minus the limit as a approaches 0 of minus a ln a, but then I'll have a negative and another negative. So I can say this is positive. If I'm going too fast, let me know and I'll slow down, because I'm doing a lot of things in my head at this point. But this negative and negative became a positive, and then this negative and this negative became a positive. So 1 plus limit as a approaches 0 of a ln a, right? But here's the problem. We still can't do this. We still can't do this limit. Why not?
Because a would be 0.
0, and then what about ln a? Ln a is ln of 0 is infinity. So what is 0 times infinity?
In 0.
That's indeterminate.
Oh.
Right? Because 0 times infinity, remember, it's one of your indeterminate forms. So how do we deal with, if I have a limit of something that's indeterminate, how do we go about doing that? We have a certain rule by a French person named, yes, L'Hopital, exactly. So we're going to do L'Hopital's rule. using limit as a approaches 0 of a ln a. So how can I write this in a way that I can use L'Hopital's rule? Well, I have to have a ratio. So what I'll do is I'll just make this real easy. Oh, no worries, Alina. All right, I'll record this so you can always go back. All right. Do you have to go too, Gautam?
Oh no, I was just saying bye to Alina.
Oh, okay. All right. So limit as a approaches 0, we need to write this as a ratio. So we can do ln a on the numerator and then a on the 1 over a on the denominator. Do you see how I wrote this as a ratio? That's the goal. We need to be able to write this as a ratio. Now what we can do, we know that this is indeterminate, so we can differentiate both the top and the bottom. So we'll have the limit as a approaches 0 of 1 over a divided by negative 1 over a squared, because I took the derivative of the top and the bottom. And if I do this, I can simplify this a little bit. This is going to be the limit as a approaches 0 of 1 over a times negative a squared, right? Because I'm multiplying by the reciprocal of the denominator. Okay. Now an a will cancel, and then the limit as a approaches 0 of negative a is just 0. So this whole thing actually goes to 0. Thus, the area is actually finite and it's equal to 1. That was quite a bit, right? Just for one problem.
That makes more sense. I was
MG, sorry to interrupt, Shruti. Just quick question. Can you,
Sure.
can you scroll? Okay, right there. Yeah.
Right here,
So
yes.
how did you get ln of a over 1 over a?
Okay, so this was it's a times ln a. Think about it like this. Let's always use concrete numbers when we get confused. Something like if I have 5 times 3, another way I can write that is by saying 5 divided by 1/3, because this is essentially the 5 times 1 over 3. That's
Right.
what we're doing. We're multiplying by its reciprocal, right? So 1 over 3 is just 3. So 5 times 3. So that's what we're doing here. Whenever in L'Hopital's rule, whenever you have an indeterminate form, and whenever you have indeterminate form and you're trying to use L'Hopital, but it's not a rational function, you make it a rational function by dividing by its reciprocal.
Okay. All right. Thank you.
Yeah. Okay.
I have one other question about, so like for improper integrals, I think you asked Raja about this, but so when you're doing like the multiple choice, you can leave the infinity in, right? But when you're doing
because they're not going to check your work, and this is why I think these are annoying, because if limit as a approaches 0, limit as a, it's like, okay. Yeah, I get it. I know it's the limit as a approaches 0. So yeah, when you're doing free response, you have to do it because that's proper math. All right, I think we should do problem B because it combines a volume question with improper integrals, and I think that would be good practice. Do you guys want to do that? I know these are taking up time, but if you can do a problem like this, I would say you're pretty much good, because these are pretty hard problems right here. Okay, everyone have this down? And of course, you can always go back to the recording, but I will go ahead and erase this. We can obviously keep our function there. Okay. Okay, all right, so let's go back to our brush. Now determine whether the solid generated by revolving region about the y-axis has finite volume. So always, whenever you're doing volume, always do a sketch. Even if you think, yeah, I can do it. No, do a sketch. It always will help you. So remember we said ln x looks like this. So negative ln x will look like this. And we're only concerned about 0 to 1. So we're only concerned about this region from 0 to 1, but we're revolving around the y-axis, right? Not around the x-axis. We're revolving this around the y-axis. So think of this in your head. You're going to have a little, kind of like an upside down vase, kind of, right? Once you revolve this around the y-axis. So we're going to determine whether this solid generated is going to be finite volume. Now, if this were x, if they asked us to revolve it around the x-axis, we could use the shell method. But, so here's the thing, I don't know if you guys know this, but when you're using shell method, your dx has to be parallel, your differential essentially, your dx has to be equal to whatever you're revolving around. That didn't make sense. Let me clarify this. If you're using shell method, and you're revolving around the x-axis, you have to be in terms of dx. if you're in shell method and you're revolving around the y-axis, you have to be in terms of dy. If you're revolving around y-axis, you have to be in terms of dy. Now, if you're using your shell method, sorry, I'm so sorry, this is disk. I always get confused with the names. This is disk. So if you're going to use disk, think about it, right? If I'm going to use disks and I'm revolving around the x-axis, I want my disks to be dx's. However, if you're revolving around y-axis, you want your disks to be dy. When you're doing shell method, you want it to be the opposite. When you're revolving around x-axis or anything parallel to it, you're going to want dy's. And whenever you're revolving around y-axis, you're going to want it to be dx's. And that should make sense, because if I'm revolving around x-axis, I'm essentially taking shells, right? The shells are dy's, dy, dy, dy. Whereas if I'm revolving around y-axis, the shells are dx's. Visualize that. Think about that for a second, and then when you're ready, let me know to move on. Because if you get that locked in your head, you should. I mean, this makes a lot more sense. You guys good? Okay. All right. So we're revolving. So we can actually do this two ways. If we wanted to use disk method, we would have to use dy's, which we can do if we convert this to a function of y. But we can also use shell method and then use dx's, right? What would you rather do in this case? I think let's use disk method just to show how we can do it if it doesn't match our condition. So shell method in this case would be dx's, right? So we would just take, I'll write down the formula for shell method so you know how to do it with shell method if you wanted to do it. This would be 2 pi times the integral from 0 to, oh, sorry, I have to put the limit. 2 pi times the limit as a approaches 0 of the limit of a to 1 of negative ln x, so I brought the negative out front, ln x dx, and then you have to put the x in the front as well, because the shell method uses the x, because it's, remember, shell method, I don't know if you guys realize this either, but shell method, you're taking circumference. Circumference is, you're taking the lateral surface area of a cylinder. Have you guys thought about that? When you're taking shell method, you're taking the lateral surface area of a cylinder. The lateral surface area of a cylinder is 2 pi r h, right? Right, 2 pi r times h. Yep, 2 pi r h. Your h is just your, let's see, 2 pi. Your r is the x times, yeah, x, and then your h would be the function, I believe, right? Because let's think about this. You have a shell that looks like this, and yeah, the r would be, the radius would be your x, and then your height would be the value of the function. So this would be f of x. So this is x, and then f of x. And since you're adding infinitely many up of them, you have to add the dx at the end. This is why we have a 2 pi x ln x dx. Okay, so that's just kind of the intuition for why we do shell method. For disk method, you're using the area, or the volume of the cylinders. The volume of a cylinder is pi r squared h, right? It's pi r squared h. Pi is just pi. R squared is the function, f of x. That's why we take f of x squared. And then your h's, your heights, are your infinitely small changes, so that's dx. That's why we do that. If you understand that, that's great, I think. So if you want to do shell method, this is how you would do it. But I don't want to do this because, as you can see, you're going to have to do integration by parts, but like a secondary step. So it'll just be a little bit more complicated in my opinion. Now, if we wanted to use disk method, we are rotating around the y-axis. So that means we have to make it in terms of dy. So whatever we do, limit as a approaches 0 of the integral from a to 1, whatever we do, it's not going to be a to 1 anymore. It'll be dy. And whatever is in your integral in your lower and upper bounds, it has to be in terms of dy. Right now, we have y equals negative ln x. So we have to turn this into a function of y. So how do we do that? We know negative y equals ln x. And to get x on its own, we say x equals e to the minus y. So now that we've solved for x, we can actually write this as a function of x. So this is now going to be e to the minus y, and because we're using disk method, this will be squared, right? This is going to be squared, and now what is our lower boundary going to be? Our lower boundary is actually going to be infinity, right? Or sorry. Let me think about this for just 1 second. It'll be, we're going from 0 to infinity, right? E to the minus, what were we doing earlier? No, we are going from infinity to 0. Because we're going from y equals infinity to y equals 0. Does that make sense? And now a is no longer 0, it's the limit as a approaches infinity, right? And then this will be the a. All right, do you understand what we just did there? And of course we have our pi. Or no, if you're confused, that's okay. Just let me know. That way I can kind of address where you're confused about.
Okay, I understand what you did for the bounds, but on the answers it says from infinity, or from zero to infinity.
So, oh, it said from 0 to infinity?
Oh wait, I might be wrong.
No, it might say that, in which case I might be wrong, and maybe yeah, I might just be having a problem visualizing it. Does it say 0 to infinity in the answers for this method?
Yeah, it does.
Okay. If we do infinity to 0, that means whatever answer you get it'll just be the negative value.
Okay.
So I don't know if AP will be okay with that. What I do is if I end up getting a negative volume and I know visually I did everything properly, what I just do is I put an absolute value sign in front of everything. That logically, I think that's okay. I don't know if AP would think that's okay, but in my opinion, if this turns out to be a negative answer, then all I'm going to do is I'm going to put an absolute value sign in front of it because the volume is always going to be positive. So that's what I do. But okay, if the answer says it's 0 to infinity, let's go ahead and try that. 0 to infinity. 0 is not going to be the problem anymore. The problem is going to be this infinity, right? So now we're going to say this is the limit as b approaches infinity. And of course, we have our pi, because it's pi r squared. Okay, does that make sense? And then, of course, this will become a b. Does the setup make sense, what we just did? Okay. All right. So now let's go ahead and calculate this. This is equal to pi times the limit as b approaches infinity from 0 to b of e. Actually, hold on. I'm so sorry. Did I set up the balance properly? Because if I have, this is 1 over e to the y. Yeah, I'm sorry. I didn't do this properly. I don't know why I doubted myself. Pi of limit as b approaches infinity of integral from 0 to b of e to the minus 2y. Oh, whoops. Minus 2y dy. We can do a quick u substitution in our head. I'm not going to write this u substitution down because on the AP exam, you're not going to have time or space to write this down. The antiderivative of e to the minus 2y is e to the minus 2y. But then if we differentiate this, we're going to get a minus 2y in the front. So this is essentially minus times minus 1/2. You see what we did? You're doing a u substitution, but you're not going to think of it that way because you don't have time to think of it that way. Right? You're doing the antiderivative. Shruti, are you good with that, what we just did?
Yeah.
Okay. And then the other thing is, whenever you see a constant, you can actually pull that out. So I can just write minus pi over 2 over here. And we're evaluating e to the minus 2y from y equals 0 to y equals infinity. Or, sorry, b. I forgot to put limit as b approaches infinity here. Okay, sorry about that. I think that makes sense. Okay, now we're just going to evaluate it. Negative pi over 2 times the limit as b approaches infinity of, this time I'm going to get rid of the minus sign and I'm just going to write it as 1 over e to the 2b minus 1 over e to the 0 is 1, correct? Okay, now if you do this, e to the 2b, since it's in the denominator, as the denominator goes to infinity, this will go to 0, correct? And of course, this is just minus 1. So the answer here is just pi over 2. Is that what the answer key says, Shruti?
Yes.
Okay, good. So that means the volume here is pi over 2. So if I had done infinity to 0, I would have gotten negative pi over 2. And simply all I would have done was just put an absolute value sign in front of all the work that I did, and then I would have gotten the same. Okay? Now, but be careful, because I don't know if AP is okay with that. Honestly, it's very hard to tell what AP is okay with and what they're not okay with. If you understand how to do this, honestly, I think this is literally everything we've done. Pretty much. Think about it. The only thing we might have not done was partial fractions. We've done improper integrals in this problem. We've done L'Hopital in this problem. We've done this method. We've done shell method. We've practically covered everything. I mean, these two problems were really good problems in that respect. All right. Anything else you guys want to cover? Any other problems you guys have that you want to go over?
I have like a general question.
Yeah, sure.
So like whenever we're doing, so you know, like the function dy over dt is equal to ky. Once you integrate that, it gives you the formula for exponential growth. So whenever I'm doing that, I get to the point where it's like e to the power of kt plus c. You break that down, you have e to the power of c times e to the power of kt. So I see that the problems will convert the e to the power of c to the constant c, right? Like they turn it into a constant. My question is like, how do we determine that constant is like the starting point, or like the initial p-value?
When you have y equals c e to the kt.
Yeah, how do you, because that c
the
constant
c is always the starting value. The c is all. We're not writing this as e to the c, because as soon as you think of this as e to the kt plus c, that makes it confusing. We don't want that. So we're going to just bring that constant out front. This is technically e to the c1. It's e to the some constant.
It's into a constant.
Yeah, but why think of it that way? That's more complicated. The reason why this here is the initial value is because whenever t equals 0, the e to the t becomes 1, because e to the 0 is just a 1. So at t equals 0, y equals c.
Okay.
Okay? All right, yeah. Honestly, sometimes you don't actually always have to use this. You don't always have to use e to the power. Sometimes what you'll notice is your ratio isn't actually e. Your ratio, you can think of it as a geometric series, or you can think of it as an exponential function, where the common ratio is something like 3. That's something you'll notice if you do the problems. Let me see if I can find one. If I can find one, we'll do one of those, because that's something we need to cover as well, probably.
Maybe you could do the very last one on 7, the one about logistic growth.
Chapter 7?
Or not chapter 7, 6. Sorry,
6,
I'm sorry.
I think. Yeah, no, you're fine.
The very last question, I think.
Let me open up on the paper first so I can see what problem it is. Oh my gosh. What am I looking for? Is this chapter 7? No, this is on. Yeah, this is chapter 7. I should looking for chapter 6. The logistic growth one?
Yeah, 77.
76?
77 or
77? Sorry, I couldn't find it. There we go.
Which chapter is this?
Chapter 6, number 77.
Oh, okay. I was looking at 6.
I think we did this one in class, but this one's a good one to do just in general. This one, what I was talking about with the common ratio thing, that one might not apply, but we'll do it just because it's a good problem to do either way, I think. Okay. We'll go back to AP problems and take out chapter 6. Chapter 6 problems. Okay, all right. We're going to work through all of these because I think they're good problems to work through. Okay, now for part A, to be honest, you can do this with common knowledge without figuring out the whole function, right? However, I think just to be safe, you should always go ahead and actually integrate both sides and separate the variables and do all that. So to do that, let's go ahead and just for practice, let's figure out how to do this. So dp dt, we need to get it into the form where we have a maximum value here minus p. P needs to be on its own. If p is not on its own, we're gonna have a little bit of a problem. So how can we put p on its own? How can we put p on its own?
Could you multiply the whole, like both sides by 12?
We want to put dp dt on its own. You can do that, and you can just integrate it later when you're integrating. You can just keep that in my mind. But rather than that, just so I can see exactly what the maximum value is, I'm going to multiply by 12 over 12, which is multiplying by 1. So what I'm going to do is I'm going to be a little sneaky about this, though. I'm going to use the denominator 12 and only apply to here. And then I'm going to put I'm going to distribute the 12 here and here. And you'll see why I do that. Because now if I do p over 60, I just multiply the denominator 12 with this p over 5, I can distribute the 12 here, and this will become 12 minus p. This allows me to get p on its own. That's why we do this. Okay, now let's figure out how to integrate this. Okay, to find p explicitly. Okay, how can we do this? Let's do dp over p times 12 minus p on one side equals 1 over, it'll be dt over 60. Okay, correct me if I'm wrong. Does this look right so far? Every step of the way. If anything's confusing or you think I'm doing something wrong, please correct me. Hopefully that looks right. Okay, now I'm going to integrate both sides. Let's do the right side first because that's easiest. 1 over 60t. And we'll put our constant on this side just because it's a little easier to work with, in my opinion, if it's on this side. Here's where the problem occurs. And this is good because we haven't practiced partial fraction decomposition yet for integration. So this is perfect, introducing another skill here. How can we integrate 1 over p times 12 minus p? Well, we can break it up into two partial fractions. First will be an arbitrary a, which we'll figure out later, a over p, plus b over 12 minus p, correct? So we know that a times 12 minus p plus b times p is equal to 1. Does that make sense? We're just doing partial fractions, right? Okay, now, one way we can do this is by setting p equal to 0, right? So if we set p equal to 0, then our BP is essentially going to be covered up, and we can say 12a equals 1, and thus a equals 1/12. Similarly, what's the other number we should set equal to p to kill one of the terms? We set p equal to 0. What can we set p equal to next?
12.
Yeah, we set p equal to 12, then we can cover up this term here, and then this becomes 12p equals 1. And thus b also equals, sorry, that should be a b. B also equals 1/12. Okay, now that we have that, I know that on this side, we'll have the integral of 1/12 over p plus 1/12 over 12 minus p dp, right? So far, so good? Okay, all right. So now what I can do is, since this is a constant, I can pull out this constant. I can just say 1/12, and I'm also going to differentiate at the same time. So this will be 1/12 times, let's see, the derivative of 1 over p is just ln absolute value of p. Population will never be negative, so you can actually just put parentheses around here, but I'll just leave the absolute value sign for right now. The derivative of 12 minus p is minus ln absolute value 12 minus p. So far, so good? Does this make sense so far? Okay, good. And this is equal to 1 over 60t plus c. All right. Now we need to multiply both sides by 12 to get this fraction out of the way. So we'll have ln p. And does anyone remember our log properties? Well, how we can simplify this potentially? This ln p minus ln 12 minus p. Does anyone know how we can simplify this?
ln of p divided by 12 minus p.
Exactly, ln of p divided by 12 minus p. All those things we've been learning in algebra, pre-cal, they all come in here. Okay, so 12 divided by 60 is 1 over 5, right? Because we're multiplying both sides by 12. 12 over 60 is 1 over 5t. And then, of course, if I multiply c times 1/12, it'll just be another c, just another constant. So I can just write c. So you'll see some mathematicians writing c1 and c2, but we know it's a constant. Intuitively, we know that it's just a c constant. So now to get rid of this ln, what can we do? Get rid of this natural log. Gautam, Shruti, anyone? What can we do to get rid of this natural log?
Do e to the power on both sides.
Exactly. P over 12 minus p equals, but now we know that if we have a plus c, we can bring that c down, and it'll be c e to the 1/5 t. And we would actually stop right here if this was exponential growth, but it's not. If this were just a p in here, we would know that this is exponential growth, but it's not. It's logistic growth. So now we need to figure out how to isolate p. How can we isolate p in your opinion? What's one way we can do that? What do you think we should do to isolate p? It's not something we do a lot in algebra, but it's a very useful trick. What if we take the reciprocal of both sides? If we do that, it'll make a little bit more sense why we're doing that. If we take the reciprocal of both sides, I can write this as 12 minus p over p, and you're still not going to realize why we did this yet, but you'll realize soon enough. And then on the bottom, we'll have, or on the other side, we'll have 1c, 1 over c e to the 1/5 t. Now, the reason why we did this is now we can break this up into fractions. We can write this as 12 over p minus 1, because p over p is 1, equals 1 over c e to the 1/5 t. This implies that 12 over p is equal to 1 over c e to the 1/5 t plus 1, correct? We just move the 1 over to the other side. Now, what we can do is 12 over p equals 1 over c e to the 1/5 t plus 1. To, let's center this a little bit. To get p on its own, we're going to get p over 12. Let's take the reciprocal again. Is that the best way to do this? Yeah, let's take the reciprocal again. P over 12 equals 1 over c e to the 1/5 t. We have a lot of compound fractions. We'll break them up in the end. Plus 1. And then we can multiply both sides by 12. So p is going to equal 12 over, and this time I can just write c e to the negative 1/5 t, right? Because 1 over c will just still be another constant. C e to the negative 1/5 t plus 1. And this is our formula for p. A lot of work, but we got through it, right? Okay. So I'm just going to select this, and I'm going to move this off to the side so we can have it for future reference, because we're going to need it later. We want to actually show what the limit is. So I'm going to move this right here for our reference. And then everything else, are you guys ready for me to erase all the rest? Okay. 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 Let me know if this is too small, but hopefully it's not. Okay. So now we need to find if p naught equals 3. That means when e is 0, if e is 0, what will we need to get a 3. So when 3 equals 12 over c, e to the 0 will just be 1, right? No matter what, c plus 1. That means 12 over 4 is 3, so c plus 1 is 4. That means c is also 3. So c is 3, okay? So essentially this function right now is actually Oh, they're giving different values for not. So I'm not actually going to write this out. But logically speaking, what is the limit as t approaches infinity of p of t? Should the initial value matter? No, because in logistic growth, you're approaching a maximum value regardless of what the initial value is. What's the maximum value in this case? It's just 12. You could have figured that out from the problem, which is why I was saying that, you know, the safer way to do it is just to actually show how you get to p and then do it. But let's just take the limit as t approaches infinity of p of t to really show them that, yes, we do know how to take limits at infinity. So this will be the limit as t approaches infinity of 12 over c, which will change depending on the initial value, but it won't matter, c e to the minus 1/5 t. All right, yeah. I'm going to post the recording later, so you can definitely go over it soon. Okay, all right,
Okay,
bye,
thanks,
guys.
Henry. Bye.
Yeah, no problem. Okay, so this time I'm going to write c over e to the 1/5 t. C times 1 over e to the 1/5 t. Do you understand why I did that? It's just a negative exponent, so I can just write it as 1 over that plus 1. Now, the reason why I did this is because if I see that it's in the denominator, t approaches infinity in the denominator, this is actually going to go to 0, right? Actually, no. E to the infinity will be infinity. 1 over infinity will be 0, so c times 0 will be 0. This portion right here will go to 0, and thus no matter what I do, the limit will always be 12, no matter what the initial value of c is. So you can say for both parts, the limit as t approaches infinity is 12. You see how we mathematically showed that? Okay. All right. Now, for p is equal to 0, p naught equals 3, for what value of p is the population growing fastest? Once again, from our knowledge of differential equations and from knowledge of logistic growth, when does the population grow the fastest? When p equals what? You remember? Half of the maximum value, right? Because think about it. This is logistical growth. We're growing, and then so the portion where it's growing the fastest is at the point of inflection. And this point of inflection, if this is the maximum value m, then the point of inflection is at m over 2. So we know right off the bat that for part B, the population is growing fastest at p equals 12 over 2, which equals 6. Let me write that nicer. 12 over 2, which equals 6. We know that it's at 6. But to mathematically show that, how do we do that? Does anyone have an idea of how we can do that? What did I say here? It's a point of inflection. How do we know when it's a point of inflection? When what? This is first semester stuff that we still need to remember. What would it be equal to?
The second derivative is 0.
0, exactly. The second derivative will be 0. That means we need to find d2p over dt2, second derivative of p with respect to t. To differentiate this, or let's use this version, the p over 60 times 12 minus p. To differentiate this, we're going to need to use product rule. So we'll have derivative of the first function is what? It'll be 1 over 60 times dp dt times the second function, 12 minus p, plus the derivative of the second function times the first function. Well, the derivative of the second function is minus dp dt minus dp dt, right? Wait, do I need to put the dp dt here? No, because dp dt will just be, this is p is a function of t. I'm sorry. Let me rewrite that real quick. So it's the derivative of the first function with respect to t. Oh, wait, no, I was right. We do need to write that. We do need to write 1 over 60 dp dt. Yeah. Because this is like thinking, you know, if I had dy dx equals y cubed, then when I take the second derivative, I need to write d squared y dx squared equals 3y squared dy dx, right? Similarly, when we take it with respect to, when we do dp dt and our thing is in terms of p, we need to put dp dt here. 1/60 times dp dt times 12 minus p minus dp dt times 1/60, right? And we need to set this, and because this is minus dp dt, because the derivative of this is minus dp dt. And this we need to set equal to 0. Let's go ahead and substitute dp dt in here. dp dt is p/60 times 12 minus p. This will be equal to 1/60. Oh, I don't know what I did there. 1/60 times p/60 times 12 minus p. But then we also already have a 12 minus p, so this will be 12 minus p squared minus dp dt, once again, is p/60. But we have another 60, so I'll just put that p/60 squared times 12 minus p equals 0. So far, so good? Or did you guys get lost somewhere in the middle here? Okay, I think we're good. Yeah, feel free to let me know if you're getting lost somewhere. Okay, now what we can do is, this is actually also going to be a 60 squared. Just to simplify this a little bit, let me just write 60 squared here. I can actually factor out p/60 squared times 12 minus p. If I factor that out, what am I going to be left with? I'm going to be left with 12 minus p here minus 1 equals 0. Okay, that means when does the second derivative equal 0? Well, one area is when 12 minus p equals 0. One factor is 12 minus p. Another area is when 12 minus p minus 1 equals 0. So this will just be 11 minus p equals 0. That isn't, did I do something wrong here? I might have done something wrong because this doesn't look right. And then the other area would be where p/60 squared is 0. I think I did something wrong. This doesn't look right. Let's go back up. Let's retrace our steps. 1/60 okay, I need to erase this. Hold on. 1/60 dp dt times 12 minus p minus dp dt times 1/60 is equal to 0. Oh, I know why. Because that should be a p/60, right? Is that what we did wrong? Either way, let's just go from here and let's actually factor this out. This will be easier for us to do. Anyways, if we factor out a dp dt. So if we say dp dt, if we factor out the dp dt now, we're going to have 12 minus p/60 minus dp dt, or no, sorry, p/60 equals 0, right? This is what we're going to have. Okay, so that means dp dt is equal to 0, or 12 minus p/60. If we take the common denominator, this will be 12 minus 2p/60 equals 0. That means 12 minus 2p equals 0, which means 12 equals 2p, which means p equals 6. There we go. That's how we got it. I don't know what I was doing earlier. I think it was the 1/60 that messed us up. This is the p/60 because when you're doing product rule, it's derivative of the first function times the second function plus the derivative of the second function times the first function, keeping it intact, right? So that's why p equals 6. Okay, so that's part B. Part C is where it gets interesting because now it's no longer a necessarily logistic. It could be logistic, but not from what we know.
Would you do you just automatically assume that p equals 6 is a point of inflection? You don't have to go back and prove that?
No, but you know that, okay. by definition, when the population is growing fastest, when is it growing the fastest? So the rate of change of the population is dp dt. Second derivative of p, I know we've learned that second derivative tells us concavity, but what it's really telling us is it's telling us the rate of change of the rate of growth. So when is this growing the fastest? When dp dt is maximized. Whenever dp dt is at its maximum point, that's when the population is growing the fastest. So whenever dp dt is maximized, remember, whenever to find relative extrema, what we do is we take the derivative of the function. So to find where dp dt is the maximum, we take the second derivative of dp dt.
Second derivative method to explain when the derivative of the exponential function was at its max. So when it was equal to 0, I
Yes,
guess.
when second derivative is equal to 0.
The second derivative method, like when
Yes.
relative extrema. Oh, see,
but
that's
no, but it's not the second derivative method to say whether p is maximum. Sorry, we're not figuring out whether p is where p is a maximum value. What we're doing is where dp dt is a maximum value or a minimum value. But in this case, since p is always growing, since dp dt is always positive in this case, we're finding a maximum value for p. If you notice, that's actually where it switches concavity, where p switches concavity from concave up to concave down. But what we're doing is so think about it. The derivative is 0 here. Derivative is increasing. Derivative gets to its maximum point. Then derivative starts decreasing again and starts going. That's what we're doing. Does that make sense? That's why we're figuring out the max. You can think of it as taking d dt of dp dt. That's what we're doing. We're figuring out the derivative of the derivative to figure out where the rate of change is the maximum. Okay.
I forgot that the function looked like that, so I was thinking of it as like as a function that like just did this, just went like that,
okay.
and then I was like, wait, and then now that you did that, now it makes more sense. Okay,
good.
Thank you.
Okay, so now let's look at the different one, which is here we have to find y of t. So y of t, well, we don't know what y of t is yet. dy dt equals y over 5 times 1 minus t over 12. Just from our experience, we know that this is a t, but from our experience, getting rid of the 12 in the denominator will help. So once again, let's do our little trick that we did earlier, where dy dt, we're going to multiply by 12 over 12, so this will be 1 over 60 times 12 minus t, and this is dy dt. But this time, if you notice, we have dy dt, and we have the t here. We don't have a y here. This is not logistical growth necessarily. So to solve this, what are we going to do? Once again, separation of variables, dy over y equals 1 over 60 times 12 minus t dt, and then integrate both sides. And on this side, you're going to get ln, absolute value of y. And then on this side, I'm going to go ahead and distribute the 1 over 60. And what we're going to get is we're going to get 12 over 60, which is 1/5, minus t over 60. So if we integrate 1 over 5 minus t over 60, we're going to get 1/5 t minus t squared over 120, right? Plus c. Okay, now to find y, what you're going to do is y is equal to c e to the 1/5 t minus 1 over 120 t squared. All right, and then we know if y of 0 is equal to 3, we know that c has to be 3. So we know that y of t equals 3e to the 1 over 5t minus 1 over 120 t squared. Okay, so that's part C. This one was actually, I think, relatively easier because you don't have like there's no logistical business going on here. It's much simpler in my opinion. Okay.
Whenever, like, again, I have a lot of beef.
No, it's fine. It's fine. That's good.
with this constant c for some reason. Whenever you are performing like any like let's say you're multiplying the entire equation by something, or you're taking the square root of it, whatever, the constant c still stays some constant c, right?
Yeah, because if I multiply this whole function by 1/60 for whatever reason, if I do 1/60 on both sides, I can still write this as a c. But you have to keep in mind that the c before, if you try and work with this equation and then this equation simultaneously, it's not going to work, because this c before is not the same as this c. It's just that we're only concerned about the final value. And because we're only concerned about the final value, it doesn't matter whether the c is, we say it's 1/60c or whatever, right? Okay, so this is y of t. Now, what is the limit as t approaches infinity of y of t? Well, if we take the limit as t approaches infinity of 3e to the 1/5t minus 1/120 t squared, what can we do? Do you guys have any ideas, or do you guys want me to just go right into it? One thing, the easiest thing I do is get rid of, or put the 3 up front. That might make it a little easier, right? Yeah, it's not going to matter ultimately, but it'll just make it easier for us to focus on what's actually growing. Okay, so now how do you reckon we deal with this business over here?
Could you factor it?
Yes, but I don't think that'll help.
Yeah.
That's a good point. Always having that questioning mindset is always more important, in my opinion. Like, go ahead and try that. See for yourself whether that'll work. It might actually work. I mean, I don't think that's the best way to do it, but let's see. T over 1/5 minus 1/120t. If t goes to, you're going to get an indeterminate form of some sort, right? So it'll be infinity times infinity. I guess you could use L'Hopital, but rather than that, think about it like this. This is essentially, because e is a constant, it's essentially 3e to the limit as t approaches infinity of 1/5t minus 1/120t squared. You see that? All we did was, instead of taking the limit of this, we put the limit up here. Now what we know is that okay, now what we know is that this is going to work. Let me think. Because I think I did it a different way on my paper, and I'm not quite sure exactly what I did on my paper, but we'll see. But if we do this, what will happen? If we do this, 3e to the limit as t approaches infinity of 150t minus 1/120t squared. Well, the t squared is going to outpace the t, right? We know that the limit as, this will be infinity, and then this will just be infinity, but the answer isn't infinity. The answer is 0. How did I get 0? Let's see. Let's keep the 3 intact. Let's just say it's 3e to the 150t minus 120t squared. Here's what we'll do. Whenever you see a negative, you can bring it down to the denominator, right? So let's do this. This is equal to the limit as t approaches infinity of 3e to the 1/5 t divided by 3, or sorry, no 3 anymore, divided by e to the 1/120 t squared. Okay, does that make sense? Okay, now this is why it equals 0. Because think about it. Which of these functions will grow faster? The numerator or the denominator?
The
Which one is going to grow faster? Look at the magnitude. Is
The denominator.
3 is not going to matter
the
ultimately. The bottom one is going to go much faster than the top function, because we have a t squared here. So as it goes to infinity, this is going to go to infinity, and eventually this denominator is going to outpace the numerator. So this is just equal to 0. That's why it's equal to 0. Okay. Sorry for the confusion in the beginning. Because that would have just given us infinity. And I don't think that would have been correct. Yeah, that wouldn't have been correct. because essentially what we were actually doing earlier was infinity minus infinity. But here, this makes sense because this is clearly outpacing the top function. So this will be 0. Okay, honestly, if you've done all like just these two problems, you're pretty much covering everything we've done this semester, right? Anything else that we haven't done? Let's think about it. What have we not done? Let's go back to materials. Let's go back to integrals and see what topics we haven't covered. Integrals. Let's see. We've obviously been doing antiderivatives. We did a U substitution in there. We did that in our head, but it was a U substitution. Of course, we've been doing definite integrals. FTOC and mean value theorem, we haven't done that. If you want, we can do a problem over that, but I know it's been an hour, so I know people are busy and I want to respect your time. We've done integration by parts, right? We did integration by parts in one of them. We obviously did improper integrals. We did the area and the volumes, right, with the region, and then we did the area of the revolution. We did a differential equation right now. We haven't done Euler and slope fields. I think Euler and slope fields is pretty easy though. So hopefully you can cover that on your own time. If not, I'm always here if you want. I can even stay longer if you want me to. Either way is fine.
For Euler and slope fields, do you think that, because I know the ones on the homework were really, really long. So do you think the ones on the test are going to be as long as the ones on the
You're
homework?
probably going to have just one Euler problem if you do have any. Yeah, and from my experience on the AP exam, they don't give like all the ones. It'll be like, okay, starting at 1 and using a step size of 0.5, figure out f of 2. Like it'll just be 2 steps. On the AP exam, they just want to see whether you know how to do it. They're not trying to, there's no point in using doing this by hand. People will do this on a computer. It doesn't make sense to. Yeah.
Right. Okay.
Okay. You guys want to do another problem, or sorry? Go ahead.
I have a quick question on Euler's method. So it's f of x naught, right? Plus x naught times y naught.
Okay.
And then
okay, hold on. I need to see it. I can't. Okay.
Okay. I'm trying to make sure that all
Sure.
I understand all my variables. Okay. So it's f of x naught. And it's plus f of x times y naught.
F of x.
Or x naught times y naught.
Okay. Maham, I don't, you might be right. I'm not saying that this is wrong. You might be right. I don't know. Personally, I don't even think about it. I forget about, because honestly, remembering abstract equations, it doesn't like register. It just doesn't connect.
Okay.
All you're doing is you're just doing linearization. Do you remember when we did linearization?
Yes. Yeah.
So if I give you, let's pull up a problem. Are there any of the AP problems that have to do with that? Do you have time to stay for 4 minutes?
I have some time. There was one AP problem on, I think it was homework 6. I'm pretty
chapter
sure.
6. I see a problem. Okay.
There were 2 of them I saw.
Okay. Number 65. Go to chapter 6, number 65. Yeah, let's do that. And I'll just write this out.
Yeah.
Okay. Number 65, consider the differential equation given by dy dx equals xy over 2. Okay? Okay. And then for part A, they want you to sketch the slope field. You can just do that. You guys know how to do that, right? Slope fields, just evaluate it at each point and then plot the slope. For part B, it asks, given the initial condition f of 0 equals 3, you use Euler's method starting with 0 with step size h equals 0.1. You can also write delta x, same thing. H or delta x are the same thing. To approximate f of 0.2. Show the work that leads to your answer. So what I do is called, I use the table method. I just think this makes more sense. You do write out x, y, and then dy dx, which equals 1/2 xy, right? And what I do is I'm going to write x, our initial condition is 0. Then they want us to use a step size of 0.1. So you go to 0.1 next, then you go to 0.2. This is what I was talking about. On the AP exam, they don't expect you to go more than 3 or 4 max, I would say. Y at 0 is 3 because that's the given condition. Dy dx at this value is 0, right? Okay. Now, what you have to think is this is dy dx and delta x here is 0.1. Delta x here is 0.2. Essentially what you're doing is you're doing linearization. Your y value, do you remember when we did linearization, your linear approximation? Y minus y naught is equal to f prime of x naught times, or f prime of x really, f prime of x times x minus x naught, right? What you're doing is essentially that. Your x minus x naught is your delta x. This is your delta x. So you're multiplying the derivative by delta x and then adding your initial y. So what I'm going to do is I'm going to this is just a tangent line. Think of it that way. It's much better if you think of it that, conceptually think about it. The other way you can think of it is I have a dy dx, which is an infinitely small change in y with respect to x. And I have an initial y naught. So to find the change in y, if I multiply by some sort of change in x, I can essentially cancel the delta x here with the delta x here, and I'm going to get 3 plus some change in y to get my new y value. Conceptually, do you understand what's going on here? That's much more important. You have a change, but to find the change in y, you're going to multiply by delta x to cancel it with the differential here. Okay, so 0 times 0.1 is just 0, plus the 3 is just 3. So this is still 3. And then 1/2 of 3 times 0.1 is 0.15. Now you're going to do the same thing, 0.15 times 0.1, the delta x is what's more important, not the x itself. 0.15 times 0.1 is 0.015, right? 0.015 plus 3 is 3.015. Thus, f of 0.2 is approximately 3.01. Okay, does this make more sense? So this is how I would recommend doing it, because it's much more conceptual. It makes, there's a logic to it, I think, because you're clearly using dy dx. You're thinking about, okay, it's a linear approximation, so I'm going to treat this delta differential dx as a delta x. I can cancel it with a dx to get the new y. Y is equal to y naught plus dy dx times delta x. And that's what we're doing in linear approximation as well. We said y minus y naught, this is point slope form, is equal to f prime of x. I think someone had to leave. Zachary. All right. I think he left already. Okay. So y minus y naught equals f prime of x times x minus x naught. Of course, this is our delta x. Y equals dy dx times delta x plus y naught. You see how we get from here to here? These are saying the same exact thing. It's what we were doing earlier with linear approximation, but Euler just said, let's go ahead and use that concept of linear approximation, and let's just do that multiple times to approximate values. Okay, all right. Anything else? I think the only thing we didn't cover was FTOC and mean value theorem. But mean value theorem for integrals, all you have to remember is to find the average value, it's 1 over delta, the interval, so 1 over b minus a times the integral from a to b of f of x dx. Easy, right? And then FTOC is pretty easy. You know, you have your derivative. If you take the derivative of an integral, then you'll just get your original function. Okay? All right, any other questions before I end? Maham, anything you want to go over?
No, I'm okay. Thank you so much.
I think we've covered pretty much everything you need to know. I can't think of anything else. In essence, of course, the more problems you do, the more it'll just stick, I think. So that's my recommendation. Just do more problems and I think you'll be fine. Okay? All right. Have a nice day, guys. Bye.
Bye.